Okay, an extra drafts video presentation on the specific subject of sound. Been thinking about it, and you know, it worked. Yeah, thinking about it worked, and another piece of the puzzle was kind of solved. So I thought I'd make a video and talk about it. So, there's this concept of sound being in a medium, and then they use that as an illustration. They go, well, light's the same thing, it's moving through a medium, blah, 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 and all this kind of mush. So, it sort of relates to more interesting physics. So anyway, but you have this idea of that there's some sort of limit, like there's a limit to the speed of light, that there's a limit to the speed of sound, and I think people who are smart can figure out that those limits don't really have anything to do with each other. But anyway, it's not the same reason there's a limit. So for sound, the reasoning, I would argue, is because atoms have a certain tension between them, and they're going to decide the speed in a medium. The medium specific. It all just has to do with how tight the atoms are. So the tighter they are, the closer they are, the faster the sound will transmit through the atoms and through the substance. And the looser they are, and the more time it takes for the atom to exchange pressure, movement, the longer it's going to take, because the atoms move much slower, theoretically, than the force that's moving them. So anyway, what complicates the subject is the idea that we can hear frequencies. That you have to have a certain on-offness to a signal for it to be perceived as sound. So it's again like light, where it's sort of frequency dependent, but it can sort of be understood that that's only a time equation in a sense, and it's only because we're moving so slowly that there's a dependence on this moving, jiggling of a substance, and that if we moved quicker, then we could, or slower, however you want to look at it, we could perceive lower frequencies as higher frequencies, and the information would be more valuable. I mean, there's no point in actually feeling things that aren't likely to be signals of anything interesting. And so it's sort of why we don't see certain kinds of light, is because there isn't a lot of information that's very interesting in those light spectrums. The most interesting one is the visible light. It has the most detail, precision, because of the higher frequency, and it's not going to blow up the machine that's trying to receive it like ultraviolet might. Hard to make a device, a natural biological device, that finds ultraviolet light a good time because it's very disruptive to atoms. So anyway, I guess I'll have to draw some of this, but I could just read through it quickly first, I suppose. So I've made this argument for years that there may be some other scientists say the same thing. I haven't really found it anywhere, but it seems something they should be able to deduce, that sound is made by movement faster than sound. And I said mostly, but it's really all the time. And so no matter what you make a sound by doing, like nails on a chalkboard, what's really happening is the little pieces of my nails are flicking really quickly across a surface, and they're vibrating. They hit it and then they vibrate. And they vibrate faster than the speed of sound. And that's what makes the signal audible, and that's what makes it able to transmit, is that it's being amplified, in a sense, by the fact that it's going faster than the atoms can exchange pressure comfortably. And so they're uncomfortably exchanging the pressure, and that's why you hear it, is because it's actually have to amplify the signal before the signal can be sent. So that's really the process. So the process means you have to create enough energy to cause more than one atom to move. You have to cause a lot of atoms to move. And so you need to move a lot of atoms, and to move a lot of atoms you have to put in a lot of energy. And you can't do that within the frequency limits unless you move it very fast. So if we only hear certain frequencies, and those frequencies are pretty high, it means the sound has to come from actions that happen very quickly, and they have to impose a lot of energy very quickly to be amplified. So, all right, we'll go on to the next statement. High speed pressure, so that means something coming in fast, faster than the atoms move, generally speaking, faster than they can exchange pressure, in the sense that there's a pressure created by electrons in atoms, you could argue, and that it takes a certain amount of time. So go back to the ping pong paddle analogy. It takes a certain amount of time for ping pong balls to go back and forth. And if you move something quicker than the speed of the ping pong paddles, the ball, very fast anyway, then the ball doesn't have a chance to make many interactions. It doesn't get to hit things a lot and push them apart again. So if you push something really fast into something else, an electron into an electron, there won't be a whole lot of pressure built up because it doesn't have enough time for the pressure to build up. The longer it takes, the more the ball bounces back and forth, the more pressure it can create. And so it bounces back. So if you're going faster than the bounce back speed, then that force has to go somewhere, and it goes to other atoms is the real point. But anyway, I'll get there. Alright, high speed pressure causes pressure scatter. So I've sort of invented that term, but it just sort of means that if you go in really fast, then the pressure can't push this atom. It has to push these atoms up here, and these over here, all around get pushed. So the motion that was going this way ends up going all these other ways because there's a backup of the pressure. The atoms just can't move that fast into each other, can't move them that fast through their pieces. So there's a clog of pressure, and so the pressure goes out in all these other directions, which means all these other atoms are pushed, their electrons are pushed, and this ends up amplifying the signal. All right, anyway, involving so high speed pressure, so going at high speed, lots of momentum, means there's lots of momentum and it scatters. It can't go in a straight line anymore. You can't just hit one atom and then hits the next atom, hits the next atom, hits the next atom. That won't happen anymore. You're going faster than the dominoes can flip, so you're causing other dominoes to fall over. Alright, involving more atoms in the transmission process. So the idea is you're causing a disturbance, and instead of just it going in the direction of the motion, it's going in all kinds of directions because it's clogged. It can't go in the direction it wants to go in, or it's heading in, and so it ends up being diverted in all these other directions, which means all these other atoms start sending the same signal. It's part of a frequency, and they're all going to be sending it now. Instead of just one ray of sound, now you have a whole bunch of rays of sound. Alright. Multiplying the number of rays of sound. So this is sort of the important part here, right? They've always talked about wave-particle duality, and it's a category error. They shouldn't be saying wave-particle duality. They should be saying, or particle-wave duality. They should be saying ray-wave duality. The question is whether the force or the stuff moves in rays or whether it moves in waves. And so they've never really had the right argument, because if you had the right argument, it would be easy to decide which one it really is. It's always rays. In the ocean, in anything, it's always rays. It's always atoms hitting other atoms, and they hit them in a straight line if they're going the speed of the medium, and they hit them in a crooked line if they're going faster than the speed of the medium. And the speed of the medium just means maintaining electron pressure and position. So if they go faster than the pressure, the rebound speed, you could argue, they make all kinds of disturbance. They cause scatter. And slower than that speed, it's a straight line that the force will end up hitting atom, hitting atom, hitting atom, hitting atom. a straighter line, let's just say. The speed of sound is the maximum speed of the straight line ray. So that's just saying when you establish a speed of sound for a substance, and it's always a substance, it's completely substance dependent, that speed just means how much tension is there between the atoms. And if there's a lot of tension, then you can move a lot of stuff fast, and if there's not a lot of tension, then it has to go slower, and the more energy you put in, the more scatter you get out. Straight line ray-like transmission of movement. This is, can be illustrated in substances like wires, tight wires, or carrying sound, or a piece of steel. And the sound does travel without leaking substantially out of the wire. It goes through the wire. So there's a tendency, a willingness for this vibration to move in straight lines. It wants to behave like a ray. And it's only when you force too much into it that the noise goes everywhere, like the tuning fork. Okay, so now I can draw, I guess. Enough preliminaries. So the real argument, there's no duality. There's just an argument. Does the universe run on rays, or does it run on waves? That should be the question being asked. And in my opinion, the decisive winner is the ray. The ray is more a part of physics than anything called a wave. Alright, so let's just do some kind of illustration for the purpose of making it clearer. Alright, so what I'm arguing is that atoms, we can say they have electrons in positions, and my argument is when atoms are associated with each other, they are in fact, boy, that's not perfect. Let's see if I can, yeah, there's no good position. Oh, okay, great. Tilted, that's no fun. Anyway, so let's just say these are electrons, and these are the nucleuses. And the idea is that the tension in these atoms is established by, well, I probably should put the electrons up here maybe, by this pressure between electrons substantially, and obviously the pressure between the protons in the sense that they repel each other. And essentially, so when you bang into one electron, it sort of bangs into the other electrons in a cascade, and likewise with the protons, the same kind of effect would exist. They would have a reluctance to be brought any closer together. And that, so what you're saying is that, so there's essentially, you could just think of it as there's a force field, okay, between everything. It's radiating a force, a pressure. Man, that's dismal. Alright, let's try more light maybe. Oh, that thing will fall on me and I'll die. Ugh. Turn that one off. Turn this one on. See if that works better. I can see it really good. Yeah, works really well here. Alright, so if I stay out of the line of light, sort of better, but anyway. Alright, so there's, and what's reacting? So I'm arguing that this is always a straight line force made of a real force, blah, 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 blah. But just think of it as pressure lines, if you like. And the point is that if this speed is faster than this pressure can react, in the sense that faster than this speed of this repelling element, that these two things will end up way too close to each other, and the pressure, the momentum, won't be transferred straight. It'll be transferred in other directions, and so you'll end up disturbing other atoms. And by disturbing other atoms, they're going to do the same thing. They're going to send the pressure in all of these directions. They're going to eventually convert what started off as this little action will eventually be converted into a bunch of action in the directions, and in a sense a bunch of action in this direction through this process of taking too much pressure and then finally getting it to where it's just the right amount of pressure for it to go from atom to atom to atom to atom to atom to atom in a straight line. So, and through that conversion process, you're essentially multiplying the number of sources. So you increase the number of sources for the transmission of the motion. And by increasing the number of sources, you end up with a signal that you can hear. You know, it's loud enough to be observed. Observed. All right, now I don't have a thing to clean it with. So a pause will be necessary. That's what I should do, pause. That should be back. Okay. All right, so the point to be made is that when little things make the disturbance, okay, a small thing happens, the idea is if it's going fast enough, it's a fast enough movement, it involves lots of atoms, and so what you're really doing is amplifying. So the movement would cause a ray of sound, but it would be only one little ray, okay? It would be just as invisible as this line. And it's the idea that you want to involve as many atoms as possible making the stream of sound. And so that's what makes the little tiny thing audible. If it was just a tiny thing making a noise at the right speed, at the speed that the atoms vibrate, well then it would just hit these one or two little atoms that are the size of the object, and the sound wouldn't radiate any further than the size of the object. So you just get this little piece of sound. And what you need to do to hear it is to make it travel through a lot of atoms. So it's a lot like electricity in the sense that the amperage, forcing a bunch of atoms in the wire. So you have atoms in the wire. If I shoot a high voltage, so it's almost the inverse of electricity. If I shoot a high voltage into the system, it'll transmit right through one layer of atoms and that's it. But if I put a high amperage, that is a low voltage but a lot of volume of hits, so a lot of stuff is doing the hitting, not just one hard punch but a lot of little punches, then I'll polarize a whole bunch of these atoms, because I'll involve a whole bunch of atoms in the transmission, and that's when I get magnetism, because now I've polarized a whole bunch of atoms. So I need amperage to cause polarization of the atoms. Kind of a separate subject, but not completely irrelevant. So that's the little thing part, and then it's the big thing, like when supersonic airplane flies too fast. What it's doing is it's essentially crushing, forcing electrons to get way too close to each other. They're all springing back in all kinds of directions. They're also heading right into the plane again, okay, and then bouncing off. So they're doing lots of reflecting off the object, because the scatter is there's so much scatter. It's a huge amount of scatter of the sound rays, okay, the movement of the atoms. And eventually, though, it gets slow enough to be transmitted as a ray. That is, the momentum gets the same speed that the atoms can accept the absorption, and the atom moves. So this atom moves, and then this atom moves the same way. So then that's the transmission. That's the normal transmission speed. You haven't violated the pressure. The pressure has time to transmit the movement. So when the plane's going too fast, there's not time for the electrons to transmit the movement, and so the movement ends up going in all kinds of directions, and eventually the momentum slows down, and now it's transmitted as rays. And it has a frequency because it has bounced all over the place in here, and so it's coming out at all kinds of frequencies, and all kinds of frequencies give you boom. Alright, but essentially that's the same thing's happening for the tiny thing. Tiny thing's creating a sonic boom to create the initial carrier frequency, okay, and so it's in a lot of ways the same exact thing. It's sonic booms that are put in a certain frequency of sonic booms. It breaks the speed of sound in a regular way, and so you get the frequency traveling the speed of sound. So you get a boom, and then a boom, and then a boom. But the booms are actually made of a much higher frequency, if you could really dissect them. The higher frequency of the scatter. When it got out of the scatter and started array, and they'll start rays at subtly different times. So the sound, the vibration will move kind of jerky through the medium, but it will have the frequency information. And that's a little more detailed than you need. So anyway, the key points is that sound really does move in rays when it's moving at its highest efficiency. So when it's going its highest efficiency through a medium, it pretty much moves in a straight line. Now obviously in the atmosphere it can't move in a perfectly straight line. I still have some glare. Okay. Because the atoms, unlike a piece of steel, the atoms aren't going to be lined up really well geometrically. In an atmosphere, the atoms are going to be a little bit sloppy. So there'll be a little bit of unevenness in how this pressure moves. But it's still more ray of sound than wave of sound. Okay, so that's my proof. And solid. Yeah, good luck pointing out how I'm wrong and such. Nice of me to wish you luck, I think. So anyway, till the next time, such and so forth and whatnot.